Every engineer designing a commercial jet or an electric vehicle faces the exact same physical constraint. They need maximum structural strength to keep passengers safe, but they have a strict weight limit to keep the machine moving efficiently. For decades, you had to pick one. Solid metals provide immense strength, but carry unbearable mass. If you thin those metals out to cut the weight, they become fragile and buckle easily under pressure. This 3D cross-section shows the architecture used to solve that problem. It is a structure known as a sandwich composite, and it relies on separating the material into 3 distinct layers, 2 thin outer face sheets and 1 thick central core. Each layer has a specific job. The thin, stiff outer skins, often made of carbon fiber, resist bending and stretching. In the middle, a thick, low-density PVC foam core acts as a structural spacer that gives the panel its depth. These materials are intentionally balanced, so they share the physical burden. Because they are bonded together, the skins and the core distribute the stress, ensuring neither component reaches its breaking point before the other. To see how they share that load, look at a traditional steel I-beam. When a downward load is applied, the top flange compresses, the bottom flange stretches in tension, and the vertical web absorbs the shear force. A sandwich panel is essentially an infinite I-beam. By expanding that vertical web outward in all directions to form a continuous core, and stretching the flanges into skins, you create a structure that can handle loads across an entire 2-dimensional surface. Because the PVC foam is rigid, it eats up those shear forces in every direction. No matter where the force hits the panel, the core works to keep the 2 skins perfectly separated and stable along the neutral axis. If you bend a thick stack of playing cards, the unglued layers slide freely past each other because there's nothing to resist shear force. But if you glue the layers together, the core becomes rigid, forcing the top skin to stretch and the bottom to compress. By pairing skins that absorb tension with a core that neutralizes shear, engineers can generate a structure with immense bending stiffness while maintaining a very low overall mass. Getting those layers to function as one requires a precise fabrication process. If you place a dry PVC core onto a dry or partially wet sheet of fiberglass, the layers will peel apart and delaminate the moment they are put under a load. To prevent that failure, fabricators use mechanical force to drive liquid epoxy resin deep into the weave of the fiberglass. You have to use a roller or a squeegee to ensure the resin fully saturates every individual fiber. You can verify this saturation with a color shift. As the resin penetrates the weave, the fabric transitions from an opaque white to a completely translucent state. Any remaining chalky white patches are dry spots. These are critical weak points that will fail under stress and destroy the panel's tensile strength. Achieving 100% translucency during this phase is what dictates the maximum structural integrity of the entire lower half of the finished composite. Once the bottom skin is wet, you prepare the central spacer. Coating the bottom of the PVC foam core with adhesive resin fills the open cells on its surface, readying it for bonding. The coated foam is dropped directly onto the still wet bottom skin. This wet-on-wet contact allows the 2 layers to chemically fuse into a single unit. To close the structural envelope, a saturated top skin is aligned directly over the core. At this stage, the assembly is finished but vulnerable until it is compressed. Fabricators drape a vacuum bagging film over the entire panel and seal the perimeter with tacky tape. The tape must be perfectly flat. Even a microscopic wrinkle creates a leak that prevents the layers from bonding. Activating the vacuum pump triggers a massive shift in atmospheric pressure. As the air is evacuated, the plastic sheet rapidly shrinks and conforms tightly around the stack, compressing the layers together. This extreme atmospheric compression is what forcefully bonds the layers and squeezes out excess resin, creating a fully consolidated, aerospace-grade structure. Once the epoxy reaches its full chemical cure, the pump is turned off. The rigid panel can be popped off the mold easily, thanks to a release agent applied at the start of the process. What remains is a part with extreme flexural rigidity, high impact resistance, and the fatigue strength required to handle thousands of load cycles without failing. Engineers often choose these chemical foam cores because they are isotropic, meaning their strength is uniform in every direction. This provides a level of predictable stability that helps complex parts handle stress from unpredictable angles. These structures have their origins in high-stakes aerospace programs. For a vehicle like the Space Shuttle Columbia, cutting weight was a matter of survival and efficiency, as every extra pound required more fuel to reach orbit. The fabrication process turned simple fabrics and foams into high-performance materials capable of surviving the harshest physical demands on the planet. This lightweight composite technology has moved out of aerospace programs and into mass-market automotive manufacturing. By reducing the vehicle's mass, they were able to improve its energy efficiency and battery range. Removing traditional heavy metal didn't mean sacrificing safety. Because the core is so efficient at absorbing shear, the chassis remains rigid and protective during an impact. Today, material science is pushing into the microscopic level. Engineers are developing synthetic core topologies and 3D printed lattices to see how much more weight can be stripped away. It leads to the ultimate structural paradox. What is the absolute theoretical limit of a material's strength-to-weight ratio before the core simply becomes too light and the structure fails from localized buckling?